All right. With this video, we're going to walk through how to perform the calculations to determine the number of calories per gram of food sample. So I have here the data I collected from the lab, which included the mass of the aluminum can, the mass of the can with the water I added. I analyzed a crunchy Cheeto. So I have my initial food mass, which I again weighed this entire unit, which included the cork, the foil, the paperclip, and my Cheeto before I burned it. So that weighed 6.85 grams. I took the initial temperature of water. I took the final and the highest temperature of the water. And then I weighed the mass of the food sample that was remaining. So again, I just reweighed this entire unit on the top loading balance. And so the difference between these two masses would give me the amount of mass of food sample that was burned. All right, that's pretty much all of the data you needed to collect. So how do you perform this calculation? Remember, the goal is to calculate calories per gram of food sample. So calories of food per gram of food. And calories is a unit of heat, and heat we like to use in chemistry as the lowercase letter q. So Q food. So if I take the Q, if I can solve for the amount of heat that was released from the combustion reaction and divide it by the mass of the sample that was combusted, then I should be able to figure out the calories per gram, my final answer, what I'm shooting for, calories per gram Cheeto. So remember, that's the goal. Here's our goal. So how do we solve for the amount of heat released from the food? Because remember, we can get the grams of food that was burned by just subtracting these two masses over here. So I know how to get that value. I just need to know, how do I get the amount of heat that was released from this combustion reaction? And thankfully, we were analyzing what was going on with the water. So we know a lot about water. So recall in calorimetry that something is going to be releasing heat, and you put a negative sign in front of the Q. And what was releasing heat in our experiment was the food sample. And what was gaining the heat, so a positive sign for Q, was the water. Okay. So if I can solve for the amount of calories that the water gained, that is going to be equal to the amount of calories that was released from the food sample. And that's how I can get this top numerator value for what I'm shooting for. All right, so Q of water, the amount of heat of water, is equal to the mass of the water times by the specific heat capacity of the water times by the change in temperature of the water. So the mass of the water, the specific heat capacity of the water, and the change in temperature of the water. I've just essentially substituted in this equation for Q. So let's fill in the values we know. So I need the mass of water. So I'm going to come over here to my table and I'm going to say, oh, what's the mass of the water? Well, I have to take the mass of the can and the water and subtract out the mass of the can alone. Let's get my calculator. 104.51 minus 12.83. So I get, and there's a place for you to fill it in here, 91.68 grams. So 91.68 grams of water times by the specific heat capacity of water. So the specific heat capacity of water is either 1 calorie per gram degree or 4.184 joules per gram degree. Since we want our final answer in calories, I'm going to stick with the 1 calorie, that's lowercase letter C for calorie, not uppercase letter C for calorie, which is 1,000 like kilocalories. So calorie per gram degree, it could be Kelvin or degrees Celsius. And then I need the change in temperature of the water. And remember, over here, we took the initial temperature and the final temperature of the water. So to find the change in temperature, the equation is the change in temperature is equal final minus initial. So 53, use my calculator again, 53 minus 0.0 minus 18.4 gives me 34.6 degrees Celsius. So 34.6 degrees Celsius. If I'm looking here at my units, I've got grams in the numerator, so grams would be on top, and then in my heat capacity units, I've got grams in the denominator, so the grams would cancel. I've got degrees Celsius in the numerator, and in my heat capacity, I've got degrees Celsius in the denominator. Sorry. So that would cancel, and my final unit here is going to be left in calories. So all I have to do is multiply these three numbers together. So 34.6 times 1 times 91.68 equals 3,172 calories, lowercase c for calories. Let me take into account significant figures. I've got 4 significant figures here. This is going to be a known, so I'm not going to worry about this significant figure. And I've got 3 significant figures here. So I want my final answer to 3 significant figures. So 3,170 calories. And that is equal to the amount of heat that was released from the food sample. Because again, remember, the food sample released heat, the water gained the heat, and we figured out how much heat the water gained from the mass of the water, the change in temperature of the water, and the specific heat capacity of the water. This is, again, this is going to help me get this value up here, except for I need the unit to be in kilocalories. So here's calories. If I had a decimal point right here, to go transfer between calories and kilocalories, you can just simply move the decimal place over 3. So it'd be 3.17 kilocalories, or big letter C calorie, capital letter C calorie. And then I'm almost done. So here we are back at our goal. So back to the goal. We wanted big calories per gram of food. And I figured out the calories of the food is going to be 3.17 calories. Now I just need to divide that by the gram of food that was combusted. So I'll have to come back over here to my data table, and the amount of food that was combusted is going to be the difference between the initial mass of the food and the final mass of the food sample. So we'll go initial minus final. So 6.85 for me minus 5.38 equals 1.47 grams of food was combusted in that reaction. So 3.17 divided by 1.47 equals 2.1. How many sig figs? 3 and 3. So I need 3 sig figs here. 2.16 calories per gram. So from my experiment, that is how many calories per gram food sample I got from burning a Cheeto. If we wanted to compare that to what's on the back of the label has 160 calories for every single serving, which says a single serving is about 28 grams. So 160, this is just for funsies, 160 divided by 28 would be 5.7, 2 sig figs, calories per gram. All right, so that would be my theoretical value. That's what I should get, but experimentally I only got 2.16. There's a lot of reasons for this. Again, your calorimeter that you're using, you're going to lose a lot of the heat to the air. You're going to lose some of the heat to the aluminum can as well, and we didn't account for either of those losses. So this is okay, but let's just go ahead and calculate a percent error to just put a numerical value on how off our experimental value was. Remember, percent error is theoretical minus experimental over theoretical times 100%. So the absolute value of theoretical minus experimental over theoretical times 100%. So I've got 5.7 minus 2.16 equals that, divided by 5.7 equals this, times 100. And if I'm looking at significant figures here, my answer is going to be to 2 significant figures. So my percent error is 62% error. And I'm okay with that because I can justify where a lot of that error went to. And again, it's that some of the heat was lost to the air and the aluminum can. Those Those are two things we did not consider in this experiment.